so I wonder if I can move that thing slightly. Actually, I don't, yeah. Oh, I guess it's that. Thanks. Right, so yeah, I have 2 lectures about sub-GeV dark matter, and I'll give an overview today about the models of sub-GeV dark matter. It'll be quite broad, but hopefully it'll connect with some of the things that have been talked about in last week's lectures and also the lectures from this week. And then I'll get into this kind of new field of direct detection of sub-GeV dark matter. So there's been lots of activities in how we can extend direct detection to look for such light dark matter models. A lot of them using condensed matter systems. And that part is what I hope to give a kind of broad overview of and give you some idea of how to think about those without getting too bogged down in the condensed matter details. All right, so that's the plan. Today I'll focus mainly on sub-GeV dark matter models and then start introducing some of the theory framework in order to think about direct detection that could be, that'll apply when we start to think about condensed matter systems. And then I'll motivate why condensed matter systems are so interesting, why there's been a lot of activity on using them for this, for direct detection. So unfortunately, I won't cover any of the other aspects of detecting sub-GeV dark matter, like with accelerators, but hopefully that will be covered in some of the later lectures. Okay, and then in tomorrow's lecture, I'll go into a little bit more depth on the condensed matter systems that have been proposed. Right then, to get started, I will start with the thermal relic cross-section, which covered quite a bit last week. And this was for S-wave annihilation. So in particle physics units, in order for Canada to give us all of the dark matter abundance, the annihilation cross-section should be 1/10⁹ GeV squared. And let's just take a very kind of generic kind of annihilation to standard model fermions through some vector mediator, which I'll call V. So I want to just explore the implications of requiring this cross-section for a simple model like this. So the matrix element squared for this will have some couplings, which I'm going to call G, chi, and GF for how this vector is coupling to either the dark matter or the standard model fermions. And there's going to be order 1 factors, which I'm going to drop everywhere. This is just to give a general argument. And this vector mediator propagator, and then I have the dark matter mass to the 4th for the correct dimensions and the non-relativistic limit. So if we were to take the point of view that we would like this mediator to be connected to, say, the weak scale, new physics at the weak scale, then we might take the limit where this is a heavy mediator. So I'll take heavy mediator, meaning it'd be much greater than the dark matter mass. So at various points, I will be using heavy and light mediator in different contexts. So right now for annihilation, heavy means heavier than the dark matter mass. Okay, so then the annihilation cross-section will be roughly, turn these into alpha chi alpha m. M chi squared over mv to the 4th. So then let's go back to the possibility of a weak scale mediator, by which I mean, say 100 GeV or maybe even up to TeV. And I might also take the coupling of the mediator with a standard model to be similar to the weak coupling, just say 0.03. So if I plug that in and I compare with the desired cross-section, what I'm going to find is something which is, give me this 10 to the 9 GeV squared, and then it scales with dark matter mass squared. Also depends on the ratio of these couplings, on those specific couplings. Okay, so what this exercise is telling us is that if we plug in these weak scale couplings and mediators, then we're left with the alpha chi or alpha x and the dark matter mass squared. And I've written in terms of dark matter mass over GeV squared. So as the dark matter mass is going below the GeV scale, this annihilation cross-section will be too large compared to the desired one for a thermal relic. Okay, so what that means is we need lighter, so sub weak scale, mediators for sub GeV thermal relics. This is often called a Lee-Weinberg bound. Just because originally there was a paper by Lee-Weinberg looking at, well, they were looking at leptons, some proposed leptons with dark matter in particular, but in any case, the argument is about the same. If you have a weak scale mediator, this is simply going to be, this dark matter can is going to be overproduced if it's too low in mass. And so that's kind of our starting point. We need to have some new mediators in order to get this thermal relic. And that means we need to extend the standard model with new mediators that are relatively light and relatively weakly coupled in order to evade all the kind of existing bounds we have, the possibility of physics below the weak scale. Yes, question?
Yeah, so I don't know if this is an order one factor that we're dropping, but for weak scale masses, I would have expected you to have something like mx over 100 GeV in there.
So the weak scale masses is going into the MV here. So then that's turning into like 10 to the 2 to the 4th becomes this 10 to the 8, that roughly.
Okay.
So that's where the 10 to the 9 is coming from here.
But I mean, even with this, don't we not, we already have sub GeV or sub weak scale dark matter if we say mx is 1 GeV, right?
Mm-hmm.
And we can still have weak scale cross sections or couplings, and we still get the right thermally average cross section.
Right. Should I wait for? Yeah, so maybe your question is like, this seems to naively work for GeV scale just from this thing I'm writing. Right. I guess what I'm arguing is like, if you go below the GeV scales, you keep going below, the scaling implies that that will fail. So I'm dropping a lot of order one factors that tell you whether it work like exactly at GeV, but definitely the scaling is the important part that you go below.
Thank you.
Yeah, it won't work.
I just wanted to clarify, did you, did you plug in alpha F is about 0.03 for this cross-section? Because we still have a factor of alpha F.
Yes. Yeah, exactly. This is, let's assume it's alpha weak here.
All right, thank you.
Yeah. right, so that's the conclusion. I want to draw a new weak scale. Sorry, new sub-weak scale. Mediators needed. And this is specifically for thermal freeze out. I know you've talked about other production mechanisms. And we'll get to that as well, but generally for thermal freeze out, new weak scale mediators are needed, sub-weak scale mediators. And I do want to add the point that my argument, the argument we just discussed was for a heavy mediator, but the standard model photon is also not allowed as a mediator for freeze out. So in that case, the scaling of the cross section would be a little bit different because obviously there's no mediator mass that's expected to appear, but instead it would go something like the charge of the dark matter squared over dark matter mass squared. And so you could consider a dark matter candidate with some small electric charge, and we'll definitely return to that. And this will, again, setting this to 10 to the 9 GeV squared, this will require some charge, say 10 to the minus 3, around 10 to the minus 3. And that's excluded by various CMB bounds. So it's excluded by dark matter baryon scattering. Dark matter proton scattering. And searches for, so that affects the CMB. And so that's a very strong constraint on the allowed charges. Yes?
Could we have some fraction of the current density be these milli charged particles and then the rest made up for with something else? And then maybe that Q could be lower so you can make these bounds?
Yes, so there's this is true for freeze out if you want to have all the dark matter be these charged particles. So there's, of course, there's a couple of exceptions. One is the one you just mentioned. We could have a fractional amount. Indeed, if you have, so if you just take the uncertainty on the baryon fraction we have roughly, I don't remember the exact number, you could have, say, 10 to the minus, I think it's a 0.2% or something, and the charge can be very large. You could have 0.2% of the dark matter be a charged particle with a quite large charge. And another possibility that I'll return to is freeze in is possible. So I'll just mention that here. So freeze in of charged dark matter is still allowed because there you're you don't need such a large charge. The charges are actually more like 10 to the minus 9 or 10 to the minus 10, and that is a allowed model that we'll return to. Okay, so now let's say we accepted the fact that we need a new mediator, and it's going to be light. And in particular, let's make it such that the mass of the mediator is now quite similar to the mass of the dark matter. And this is kind of a light mediator from the perspective of this is kind of a light mediator in the sense that it's light relative to all the stuff, the standard model stuff at the TeV scale. And now we have additional channels that could open up in terms of annihilation. So you could have annihilation directly to the mediator, sufficiently if it's lighter. Okay, so if we go back to the estimate of the cross-section from this previous slide, so we have this estimate which for a heavy mediator. When the mediator is relatively light, then we can just replace this MV. When it's similar or lighter than the dark matter mass, we can replace the mediator mass in the bottom with the dark matter mass itself. So this was for direct annihilation to standard model. As I was just saying, we also have a process like this where you could annihilate directly to the mediator, and that's going to have a similar mass scaling, but a different coupling scaling. So whichever one of these processes is larger is going to dominate the freeze out process. And again, if we compare that to this 1/10⁹ GeV squared, that can tell us something about the couplings of this new mediator that we want to introduce. So it's going to be either this combination or this combination. So I'll just write it as the max. Of course, it depends on which are kinematically allowed, but this is again at the order 1 level. So the combination of those couplings has to be 10⁻⁵ times the dark matter mass over GeV. So again, I'm getting that from setting this to 10⁹ GeV squared. And so what that's telling us is if we include this light meter, it's going to have pretty small couplings. It depends on which of these dominates, but overall this combination is at most 10⁻⁵ roughly when we're at the GeV scale. And as we go lower in mass below the GeV scale, this is going to become smaller and smaller, of course. So we're looking at light, not weak, but say feebly, somewhat feebly. Not weak in the sense of weak scale. We're looking at light, feebly or weakly coupled mediators for sub-GeV dark matter. And this gets into the big picture of dark sectors. Where we have this dark matter, we have this mediator, and they might be at a similar mass scale. They don't have to be, but they might be at a similar mass scale. And the communication of this mediator with a standard model is through this very small coupling. Yes.
Is it possible in these models that you could be coupling to the standard model weak force?
So the vector mediator, or this in this example, the mediator itself cannot be like a weak gauge boson. So that's what this argument is saying. It can't be a weak gauge boson. Do you? Yeah, if that's.
That makes sense. I think I was thinking about it wrong.
Okay,
Thanks.
sorry. Yeah. Right, and so the most commonly studied new mediator is that of the dark photon. And so I want to spend some time getting more into dark photons, which we talked a lot about yesterday. Okay, so this is the most commonly studied one, and I will write it as a V. There's different notations. Sometimes it's called an A prime. And so F here is the standard model photon, V is my dark photon. And the way this is usually introduced is with a kinetic mixing between the standard model photon and the dark photon, which is called epsilon here. It's also sometimes called kappa. And this dark photon potentially has some mass, mv. This is usually just inserted as a Stueckelberg mass. It's just a U1. The kinetic mixing is a free parameter, and it's thought to come from, or the idea is that it could come from, say, some loop of some heavy particle. that couples to, that's charged under both the dark photon and the standard model photon. And if that's the case, you can generate pretty small kinetic mixings depending on how many loops you have to go through in order to, or depending on how many loops you have to go through in order to get this communication between V and A. You can get 10 to the minus 3, 10 to the minus 6, so on. All right, and then this dark photon could couple to the dark matter. Here, I'm just denoting this as a dark current, so it could be some chi-bar gamma mu pi. And there are two important bases for this dark photon model. So of course, you can deal with the dark photon model in any basis you want, but it's useful to kind of do a change of bases in two particular limits. So the first is where the dark photon mass is relatively heavy. So what I mean by that is it's definitely, well, if we have a non-zero mass, and in particular, that means the dark photon mass is actually larger than the in medium photon mass. So what I mean by that is, of course, in a vacuum, the photon has no mass, but if you're in a plasma, then in general, there can be some finite photon mass. Basically, you can think of it as an index of refraction of any material. The speed of light gets slowed down so that there's a finite photon mass. So depending on the situation you're in, there will be in general a very small photon mass. And so the real comparison is whether the dark photon is heavier or lighter than that. So let's take it to be heavier than that. And this would apply, for instance, if you were thinking about MeV or GeV scale dark photons. Let's say MeV GeV mass. So generally, photon mass is irrelevant in that case. In this case, we can define a basis to get rid of the kinetic mixing. And so we can define a new field, which is the photon field minus a small mixture of this dark photon field. And the reason we do that is there's no photon mass, or basically the photon mass is negligible. So if we make this definition, the only thing it does in terms of the kinetic terms is from here, it'll introduce an additional term which will cancel off the kinetic mixing. So basically we would get just decoupled kinetic terms plus, well, this mass remains the same, and now what happens is that the coupling of the photon here gets replaced with coupling of the this redefined photon and the dark photon. Right, it's a bit squish. Okay, so this part is basically just the standard kinetic terms. For epsilon being small, this is not too important. You can get rid of it. And the leading contribution at order epsilon, which is a small parameter, is this coupling of the dark photon with the standard model fermions. Charged standard model fermions. Okay, so yes, question?
So then, what's the motivation for this change of variable?
Right.
sorry, I'm a bit lost. What was the motivation for these changeable variables?
Yeah, so the reason I am introducing these change of variables is that this kinetic mixing coupling can be a little bit confusing to deal with. So it's easier in this limit to think of just a dark photon being coupled to the standard model electromagnetic current. And what we'll see is now if we take the opposite limit where the dark photon is very light, it's the opposite case. We can think of dark matter as being charged under the photon. So if the mediator is very heavy, we can kind of skip this kinetic mixing one, which is a little more difficult to work with, I'd say. And just think of all standard model particles being charged under a new dark force and work in that basis.
And another nice question.
Keep going.
Oh.
And another nice question, like what is the symmetry leading to this Lagrangian? Because this mass term breaks U1, right?
Can you maybe repeat the question?
Oh, yeah. This Lagrangian breaks the U1 by including the dark photon mass. Yeah, that's right. So this is really, you can think of as there is some Higgs, but it's very heavy. It's integrated out. Yes.
So you motivated this change of basis by saying this MV is greater than the photon mass. But couldn't I have just made this change of basis regardless of the mass splitting there?
Right. So let me actually do the next case now where the dark photon is lighter than the photon mass. And we actually want to do a different rotation in that case.
Okay. I may ask my question again.
Yeah, so the reason that we did it, I'm doing it this way is because there's no photon mass term effectively. So if I do this, if I were to do this rotation on V, then you would see that I would actually induce some additional terms, mass terms for the photon.
I see.
If I were to do a similar rotation on V.
I see.
Yeah, so whichever one is lighter, that tells you you should rotate that one, basically. Yeah. All right, so now let's do the opposite limit, which is basically if it's much lighter than the photon mass. You can think of it as a massless dark photon, but the way I'm thinking about it is it's much lighter than an in-medium photon mass. So as we were just saying, this tells us we want to do the opposite rotation, which is we rotate the dark photon to have a little bit of the photon. And so I won't write all the kinetic terms, et cetera, again, but if we do it this way, then you see we have the following interactions. So in the first case, we have standard model is millicharged under dark photon. And in the second case, what we see is that the dark matter is millicharged under photon. Yes, question?
Yeah, in this second case, if both of them are massless in the vacuum, why does this limit have any meaning?
So yeah, the question is if both of them are massless in the vacuum, does this have any meaning? If they were both exactly massless, then I would still take this second case, if that's your question. And if there were no dark matter, it would have just no meaning at all because it would be like a redefinition of the photon. It's only because I've specified that there's a dark matter which couples to one of them that it gives it any meaning, basically. Yeah.
Thank you.
Yes, question?
So will there be like some sort of Cherenkov radiation in the dark sector or?
Would there be Cherenkov radiation in the dark sector?
As in, whenever I see something that is like charged and travels faster than the photon in that medium, then I think, oh, Cherenkov radiation.
I think there could be, but the couplings in the dark sector are pretty small, so that might not be, yeah, very,
Observable.
yeah, large effect. But I don't know if anybody has studied that. Yeah, it's an interesting question. All right, and so in this second limit where the dark matter's millicharged, the charge of this dark matter is this combination of couplings of this dark sector coupling epsilon relative to electromagnetic charge. Okay, so hopefully this will give some intuition for what I'll show next, which is a whole bunch of different constraints on dark photons. So this is collected constraints. I mean, 2019, there might be a few that are out of date, but it's not too important for the moment. We just want to get the broad features. So this is the kinetic mixing versus the dark photon mass over an enormous mass range. And if we look over here, so this is MeV, mass scale. So almost all of the constraints up here are coming from this searching for basically this, the way we think about it is, again, you could look for, say, a decay of this into E plus E minus. So a lot of the accelerator constraints, for instance, are coming from looking for that particular coupling where you can produce the dark photon and might decay back to E plus E minus. Similar for the supernova constraints up here. But in the limit in the opposite limit where we take the dark photon to be much lighter than kind of plasma masses, you see an interesting effect where these constraints are all becoming a lot weaker. So what are these constraints from? They're from looking at the emission of this dark photon inside various kinds of stars. So this is Sun, horizontal branch, red giant, they're just different kinds of stars. And in each case, you can emit the dark photon and it could escape and it would lead to some cooling of the star. But as we were just discussing, if the dark photon becomes more and more massless, then we're in this second limit where only the dark matter is millicharged under the photon. And so if this dark matter is actually not present, or maybe it's too heavy to be produced, then the emission decouples. So this is basically why all these constraints get much, much weaker. When there's no dark matter, so let me just make that clear. This assumes no dark matter. So this is just looking for the dark photon coupling. So when we're in the second limit, if there was no dark matter, then basically there would be no effect of this dark photon. And all these constraints should go away in the zero mass limit. And that's what is reflected by this fact that all these constraints are getting much weaker. Yes.
Sorry, I just got now a bit confused. So,
Oh,
yeah.
Thank you. Okay, so I got now a little bit confused. So we say, okay, so it's no dark matter. Okay, sorry, I was, no, okay, everything clear.
Sorry, yeah, strictly speaking, all these constraints are derived ignoring the dark matter coupling. So just crossing that out.
Sorry.
Yeah, I have a couple of questions. First, why does BDM give you this sort of island constraints? And the second one would be if you can explain about this test of the Coulomb force constraint dark photon, because I never understood that. I'm very interested.
Yeah, so I don't want to go into all of these constraints too much, but yeah, I can say a little bit about each. So these islands, these are coming from producing the dark photon out of the thermal bath, and then they decay again, I believe. So because that's like a combination of effects, then it's only really sensitive to particular islands. Because if you produce enough dark matter, sorry, if you produce enough dark photons that they thermalize, that's different than this scenario. This scenario is looking at out of equilibrium production of dark photons, and so it's very sensitive to very small couplings. So it's saying, yeah, very rare out of equilibrium production of dark photons you can be sensitive to because it'll decay back later and affect BBA.
Okay, but I still don't understand the idea. Okay, I guess it's not trivial.
It's yeah, it's that particular effect. Yeah, that they're sensitive to.
Coulomb, if you know that.
The Coulomb one is that is kind of like a fifth force search. I don't remember the details of this one. It's actually a very old experiment. It's probably 50 years old or something, but it's a kind of fifth force experiment, because there is still some very small residual extra coupling that depends on the dark photon mass here at, say, if it's 10⁻⁷ eV, then they would look for some fifth force, which has a Yukawa potential, which is not a 1/r² Coulomb force.
Oh.
Yeah, yes.
There's a lower bound, somewhere like 10⁻�XVI or below. What are
This bound is just where I cut off the plot. There's no, yeah, there's nothing, because there's very few constraints below here, but there's no particular reason to cut it off there. Yeah, I think people have even considered lower.
You're fine with
Okay, I'll talk about. Is the island effect for BBN because of the effect of the dark photon on the different light element abundances?
That's right. So these, if I remember correctly, these islands are, you produce the dark photon out of equilibrium. So there's a very small amount. Because these couplings are so small, the dark photon takes a long time to decay. It decays at some later time and affects light element abundances.
Okay.
So I think different islands are like different light elements that
Yeah.
are being looked at. Yeah.
So I know you said you want to go into all of the constraints. Could you very quickly say why there are two supernova constraints? What's the difference between the green and the yellow?
Yes, so this supernova constraint is from producing the dark photon and then requiring, assuming the dark photon is produced and it escapes, then it will cool the star. And you can compare that with neutrino cooling, and that's this constraint. The bottom one is interesting. I believe, I have to double check, but I believe it's from the fact that now these dark photons escape and they decay to E+, E-, and you could observe the E+, E-, and I think you observe the E+, E-, and that leads to this constraint.
So is this only for dark matter that's thermally produced, or also it considers non-thermal?
This is, yeah, so to clarify, this is just the constraints on the dark photon, and all of the ones shown here are assuming there's no dark matter coupling involved. So all these constraints will change if you put in the dark matter. Well, some of them will change, not all of them. So, yeah.
Okay, thanks.
Yeah, so this I wanted to introduce, one, to highlight the fact that for dark photons, they are special because the constraints become much weaker once the dark photon mass is sufficiently low in mass. And so one of the benchmark points I'll look at is a dark photon that's kind of in this region. So this will be what I'll consider a light mediator. So again, light will mean much lighter than the dark matter in this case. So say kinetic mixing of 10 to the -6. So that will be relevant for one of the benchmarks I'm talking about. And then the heavy mediator limit will be relevant for a thermal freeze out benchmark. Okay, so just keep in mind that given all these constraints, I'm going to be looking at two possible rough parameter ranges for this dark photon, one living here and one living up there.
Sorry,
Oh, yes.
very briefly, what's the idea behind the constraints on the CMB? Is it because it behaves as dark radiation and it changes the effective number of degrees of freedom or relative degrees of freedom, or is it something different?
Yes, the CMB constraints, those, the ones I plotted are a little bit out of date actually, but they're from looking at conversion of CMB photons into dark photons. There's a resonant conversion when the photon mass passes through the dark photon mass. So that one's definitely a little older because there was a more recent paper by Josh Ruderman and others updating those constraints. Okay, so keep in mind these two. Let me just summarize what they look like then. So for this heavy meter, this will be one of the benchmarks that appears a lot, especially direct detection and accelerators. And so by that, I mean MV is similar to MChi. The dark photon is similar. And as we said in this basis, the dark photon is coupled to the standard model. So we think of it processes like this. So this could set both the relic abundance and it could mediate. Sorry, if this is a scattering, I'll make it both, or it can mediate dark matter electron scattering. So just as an example benchmark, as I was saying, you could have kinetic mixing, I'll use consistent notation, kinetic mixing of about 10 to the -4 for a dark photon mass of say 30 MeV. And we could take dark matter mass to be about 10 MeV. And you can check that this can give you the right thermal relic abundance. If you choose, of course, you have to also choose GChi correctly. I didn't write that down, but so you can choose GChi correctly. And another constraint that I don't want to get too much into, but you have the self-interaction constraints like this. So you can so that will lead to constraints on GChi, and you can check that satisfies that. So this will get around BBN constraints. It will also get around, it will satisfy all the indirect detection constraints. If we have this chi being, for example, well, for one to satisfy BBN constraints, for this to be a thermal relic, we generally require the mass to be greater than 10 MeV. That's a rough number. It depends on what spin you assign to this. But we don't want it to be in equilibrium through BBN, so that generally sets a lower bound around few to 10 MeV. And then in order to satisfy all the indirect detection constraints, then we could have this chi could be asymmetric dark matter talked about. Or it could be a scalar dark matter candidate, in which case this is a P-wave suppressed annihilation. And as I said, there are lots of proposed accelerator probes of this dark matter candidate, which I don't have time to get into, but I just want to focus on the dark matter electron scattering. So now I'll introduce fiducial cross-section for dark matter electron scattering. And it goes as reduced mass squared, the combination of couplings, and then the denominator is a reference momentum squared plus the mediator mass squared. So if you were calculating the actual scattering, then of course you would have the actual momentum transfer squared. And then what we do for dark matter electron scattering is usually define a reference momentum transfer, which you can define as cross section. And as we'll discuss a lot more later, this reference cross section is given by fine structure constant times the electron mass. And so with the dark photon mass being 30 MeV, this is much larger than the reference momentum, which is about 3.7 keV. And if you plug all these numbers in, you're going to get a cross section of about 10 to the minus 37 centimeters squared. Oh, there's a question?
Yeah, thanks. For the scalar case, does it have to be P-wave suppressed because of that self-interaction?
So the scalar case is I'm replacing this, well, I'm setting this chi to be basically a scalar field, and then it's P-wave annihilation. You can use the arguments that Tracy mentioned from looking at the symmetry properties of the initial and final states. So it doesn't have anything to do with the self-interaction cross section.
Okay, gotcha. So it's S-wave suppressed and the P-wave is the dominant channel.
Yeah.
Okay, gotcha.
Yeah. P-wave is dominant channel. Okay, so you can plug in the various numbers I gave above, and you can check that this cross section is about 10 to the minus 37 centimeters squared. So immediately that strikes us as quite huge compared to the kind of cross sections that are currently being constrained in terms of dark matter nucleus scattering for heavier dark matter. So that's already a pretty interesting sign that we could look for dark matter electron scattering. All right, the other limits that I've been alluding to is the light mediator limit. And in that limit, the dark matter is charged on the Standard Model photon. So I will replace this with the Standard Model photon here. As we were discussing earlier, dark matter, which is charged under the photon, cannot be a thermal freeze out candidate. So this is only possible with freeze in. So as a reminder, with freeze in, which you talked about last week, if I look at the annihilation process, well, if I look at this process, for instance, in the early universe, if the couplings are sufficiently small, then this process will only go in one direction because you never produce enough dark matter that it can annihilate with itself back. The number density of dark matter you produce is way too low. So there's a cartoon in which you can look at the abundance of dark matter with time, or 1/T. And freeze out looks like this. And freeze in looks like this. And so the amount of dark matter that you produce just saturates at some point. And again, you can use this out of equilibrium process to estimate the couplings you need. And in this case, you need about 10 to the minus 13. If you convert that to the charge of the dark matter, it's on the order of 10 to the minus 11, 12 for dark matter charge. So that's a viable model for dark matter just being, you can just think of it as having a really tiny charge. In practice, it's kind of generated by the dark photon through the kinetic mixing, remember, through this G chi epsilon/E. Because this dark matter candidate is never in thermal equilibrium, we are not so concerned with BBN constraints. So freeze in is viable for masses above about 10 keV. And the 10 keV comes from a combination of things. It comes from, say, warm dark matter constraints. Also, it comes from the fact that in a lot of, there are various stellar cooling constraints again. So if you have the typical star, the core temperature might be as high as 10 keV, and you can directly produce the dark matter, it'll escape, it'll cool the star. And if I go back and take the same cross-section definition, this mass down here will go away. So let me just copy it. And instead, what appears in the denominator is the reference momentum, which remember is quite small compared to the mass scales we've been talking about so far. This was 4 keV. And it turns out even if you plug in these very small couplings for freeze in, you get a very similar cross section of about 10 to the minus 37 centimeters squared. And again, this is coming from the dark photons living in that very low mass part of the parameter space of the dark photon kinetic mixing mass parameter space I showed. And as I was saying, these cross sections are really quite large. So if I were to estimate a rate for dark matter scattering by taking, say, the number of target atoms and just say there's 1 electron per atom, dark matter number density, and sigma v, just as an estimate of this rate. If you were to plug that in with the typical numbers I mentioned, well, we know the number density, we know you take this typical cross section, you would get about 10 to the minus 2 events per kilogram per second, which is actually huge. So if you had if you had a kilogram size detector, over a minute, you would be seeing every minute you'd be seeing a dark matter. event as compared to the much more rare event surges Jody's been talking about. Yes, question?
Can you repeat why this is only viable with freeze in? Can you repeat why this is only viable with freeze in? I mean, I guess I'm thinking that it kind of depends on the mass of my dark matter.
Yeah, so if this right, if I want a thermal freeze out, this charge has to be quite large. I was saying earlier, the charge has to be about 10 to the minus 3 for a thermal freeze out to work at a GeV scale. It's mass dependent, you're right. But it has been shown that for basically anywhere from KV to TeV, the charges you need would be excluded by CMB constraints on how dark matter has to be.
Thank you.
There's a question that's in there. Learning to unmute. Say,
Sorry, what do I?
is Josh doing us unmute?
Josh, just unmute yourself, please.
Yeah, hello. Okay, so just a question here about this freeze-in mechanism. So I mean, so given the huge abundance of dark matter, density and, the abundance, I mean, we would require like a lot of electron positron that are present in the early universe, much more compared than what we see now. I mean, so just two questions, like, so how would that play in the cosmology? And also, we'd also have to produce or annihilate away enough electron positron pairs to actually get a neutral universe, because, for the proton number to be equal to the electron number. So maybe could you comment on that?
I'm sorry, I'm not sure I fully understood the question. Was it? So there are a lot more electron positrons than dark matter. So it's like one in 10 to the minus 10 times or probably smaller. Only rarely does the electron positron annihilate into dark matter. Most of the time it's in equilibrium back and forth with everything else.
Okay. I mean, my question was just like, given the omega CDM today and omega matter today, the early universe, we'd have to say, is mostly just populated by these electron positron pairs. And then, for the freeze-in mechanism to work, you'd also, like, at the end of this freeze-in mechanism, you should also have the correct abundance for electrons that are produced, so equal numbers of electron when compared to protons.
Yeah, that's right. So this is one thing is this is not affecting the net asymmetry. So it's not going to affect the charge asymmetry if that's what you're worried about. But the other is that, yeah, this is very, very rare. So you're taking only a tiny amount of energy away from the electron positrons. That's what you're asking. Because there is a lot of there is a lot of dark matter today, but at the early time, you're not taking anything away really. It's a tiny fraction of the total thermal mass.
Okay.
Yeah, and it's not affecting the asymmetry either. Okay, so okay then. All right. All right, so these will be our motivating models, and I'll show various benchmark lines throughout as we talk about direct detection. Just a few comments more. So the dark photon model will feature prominently, but I'll just briefly discuss how scalar meteors are quite different. So if I had a scalar mediator, so I'll just put in a mass and some Yukawa coupling to nucleons or electrons. In this case, there are very strong constraints on the scalar mediator. So light meaning anywhere, depends on exactly the mass range, but definitely below an MeV. And that's going to come from stellar emission, fifth force searches, for instance. And the key point is that as we go to lower and lower scalar mediator mass, the constraints don't disappear like in the dark photon case. They remain as strong or they get even stronger. And so this is a very different type of model. It's much more constraining. We don't have the same Friesen benchmarks. So this is very limited parameter space. For sub MeV dark matter, because we can't get Friesen to work through that very light mediator limit. And indeed, thermal freeze-out is also quite constrained if you include all the various bounds on the scalar mediator. So that's one reason that it's not so easy to show like clear direct detection constraints for scalar meteors, and you don't see that so often. Of course, there are models with viable scalar mediators, but the prediction, the connection between the thermal relic and the direct detection is just not as sharp and clear as in the dark photon case here, where we just directly plug the couplings into the scattering cross-section. Okay, so I just wanted to mention that's one reason we don't consider this isn't shown quite as much. Yes.
Are the ends here neutrinos?
Oh, this is a nucleon. Sorry, yeah. So nucleon meaning proton or neutron.
Okay.
Nevertheless, just because there are viable models, although there's not a sharp target. So we do often consider this nucleon coupling because it's a kind of generalization of the WIMP searches where you're looking for nuclear recoils going down to lower masses. Okay, and beyond the particular benchmarks, there are of course lots of other production mechanisms as you've been hearing about, and they give other types of predictions. But the ones I'm showing about are the ones that are most often shown on plots you might see in this literature, so I focused on them. All right, so in this last part of today's lecture, I want to start introducing kind of a way of thinking about direct detection that's going to apply for condensed matter. And I'm going to start with a very general rate formula for dark matter scattering, and I'm going to show you how that gives the nuclear recoil rates that we've been talking about, and then how we're going to apply it more generally. Okay, so this is starting from as general as possible, some interaction Hamiltonian between dark matter and some target. So that's our goal. We want to look at, without specifying what it has to be, we want to look at dark matter in our halo scattering off some target system in our lab. And that interaction we'll describe by some Hamiltonian, usually in the non-relativistic limit, because we're dealing with non-relativistic particles. And if you're given that interaction Hamiltonian, then you can use Fermi's golden rule to get this rate formula that I have written down. Okay, so this first part, this is a target density. And that's just because we're usually talking about a rate per amount of target mass, because that's the convention in direct detection. That's why I've included a target density to convert it to that rate per target mass. This is the dark matter number density as seen, and velocity distribution. And then this part here is just the sum over final states. So it sums over the possible final states of the target. That's what the sum over F here is. And it sums over the possible final state of the dark matter, which is just specified by the outgoing momentum. Okay, so we'll just have a dark matter coming in, some initial state of the target, final state of the target, and this is chi prime, chi with p chi prime. And in most cases, we can, vast majority of cases, many cases, we're going to be able to just factorize this into two pieces. So one is going to be a dark matter piece. And one is going to be a target piece. This should be an integral over this for a mode Q. Yes.
Are we assuming here that we have just one species of dark matter particle interacting with one type of target particle?
So we are assuming there's only one species of dark matter particle. For the moment, we aren't saying anything about the target. I'm trying to be as general as possible and just saying it goes from initial state to final state, whether that's a particle or something else.
Okay, thanks.
Okay, so the dark matter part is easy to deal with in that we often assume that the dark matter particles are so weakly interacting, they can just be treated as plane waves for the initial and final states. And we're going to be able to write this operator for the dark matter side in terms of a cross section. Write it as this is an interaction strength, so that's why I'm putting it as the square root of a cross section. So if I were talking about dark matter electron scattering, and I'll write this more explicitly shortly, then I might think of this interaction Hamiltonian as a Coulomb potential between dark matter electrons. And that Coulomb potential would govern this, would be basically, that's what I mean by strength of the interaction potential. That would be appearing here in this combination of factors. I'll find that. Next slide. And so what that gives now is a form of the rate, which I can separate clearly into the dark matter pieces and the target pieces. So the first part is the same. So this is this strength of the interaction squared appearing here. And I can separate out the target piece in the bottom line with some operator here, which I'll define. And in order to really separate them out, so what we have is we have this energy conservation delta function, just says that of course, the energy you lose from the dark matter has to go into the system. And I'm just gonna define a new auxiliary variable called omega. And I can now factorize the target piece by writing this as omega. Sorry, that's minus omega. So I've replaced the dark matter energy though, the energy that the dark matter is deposited with omega, and then I have to introduce it back up here. Including the d omega.
I am a bit concerned about momentum conservation here. Where is it coming from?
So the only momentum conservation we have so far is in the dark matter part. So when this matrix element is evaluated, it's going to force p chi prime minus p chi is equal to q. So I do have I glossed over that a bit, but when you calculate that with plane waves, it'll force this relationship. And so I've actually replaced the dark matter final state with momentum transfer q.
But what about the momentum of the initial and final state?
Right, so yeah, that's a good question. So right now I haven't said anything about momentum conservation in the target system. And in general, it's not actually so simple because you can have, when we get to condensed matter systems, then it's not the straightforward momentum conservation actually. So that actually hasn't appeared yet. So the only thing we've said is that dark matter loses momentum or deposits momentum q, and then we're gonna just have to figure out how that momentum transfer looks in the target system. Okay, so this is a very important equation that I'm going to be using throughout next lecture. So let me go through each of the pieces. So the first part is the same. And what I've done now is instead of talking about what the dark matter final momentum is, I've just used this momentum conservation, as we've just said, to turn it into an integral over the momentum transfer. So there's two basic phase space variables we can think about for scattering. We can think about the momentum transferred by the dark matter. And we can think about the energy deposited. So for a given interaction of dark matter in the lab, we want to, that's our phase space. We want to integrate over this allowed phase space. We're going to weight it by the interaction strength and energy conservation in the dark matter side. But everything else here is actually just a property of the target system. And this is a quantity that we'll call the dynamic structure factor. Often abbreviated S of Q omega. So basically the interpretation is we have the dark matter part just in the first line, essentially, just from kinematics and the interaction strength. And then given that allowed phase space, this function S of Q omega is telling us how the target system will respond to a given energy and momentum transfer. Okay, so let me go through each of these pieces in a little more detail. So first for this interaction strength, let me just give the example, as I said, of a Coulomb potential. If it were a Coulomb potential, this is what my Hamiltonian would look like. So this is just a Fourier transform of that Coulomb potential between some charged particle and the dark matter. Well, it's a dark Coulomb potential, so it includes a dark photon mass. So that's an example for a dark photon mediator. And if you then plug this in to calculate the expectation value, as we've been doing, then what you would get is this combination of things is exactly what appears inside the sigma of Q over pi squared. So if you remember the definition I gave earlier, well, for electrons, get rid of the Q. Sorry, this D should be a X. All right, so if I have this Coulomb potential, this dark photon potential, then this overall prefactor is basically connected with the cross section, similar to the dark matter electron cross section I gave earlier. And then you're left with some expectation value of basically e to the I q dot r on this target system. So if in the target system you're dealing with, say, a free electron, then you might take plane waves for the initial and final states for this electron, and then you would get total momentum conservation. This was asked, but in general, these could be some other complicated final states.
Hey, sorry, the slide before for this formula for R, we use the famous golden rule. So in which picture is it here? Is it in the Schrödinger picture, interaction picture, or Heisenberg picture?
I guess I haven't really said what delta chi is, but it should be, I guess I'm using it in the Schrödinger picture. Yeah.
Yeah, because I'm thinking this delta H you're using in the next slide, that this is, why should this be the interaction when it's only between these particles?
Yeah, I'm using it in the Schrödinger picture. You're right. Yeah. So I guess you're asking why am I assuming that this Yukawa or effectively Yukawa potential is the one that dominates?
I mean, if you have, for example, just an interaction like in usual quantum mechanics, you do not use the Coulomb potential as an interaction as a perturbed in the domain in your formula for the famous golden rule.
Yeah, so that's a good question. I did jump to using this potential, and it's not the full potential. So if you were to start certainly from the relativistic theory, you will get additional contributions to the interaction between dark matter and electrons, which are not just the Coulomb potential, of course. But in the non-relativistic limit for dark matter electron scattering, this is the one that dominates. So similar to charged particle scattering, like Rutherford scattering, it's the Coulomb scattering that dominates in this limit. And the same is basically true here. You have additional corrections, but they're smaller by roughly the dark matter velocity because because you get them from the relativistic theory.
Other questions?
Okay, so there's not that much time, and the last thing I want to talk about is this. So we've covered in this main rate formula, we've covered this interaction strength now. And the last thing I want to cover is just the kinematics of the dark matter phase space in terms of this Q, omega, and energy conservation. Okay, so I've written in terms of the final and initial dark matter energies, and for just free particle non-relativistic, I can write the delta function as 1/2 mv squared. That's the initial dark matter velocity. And then the final dark matter momentum is just the initial one minus this amount that was lost over 2 mx. Yes?
So with these light mediator and dark matter particles, looks like you're assuming it's non-relativistic. Like, does that break down at some point, that assumption? Like, could it be warm?
So there are, there are contributions to the dark matter flux that could be relativistic. And that would change that would certainly change everything I'm talking about. I'm just focusing on the halo dark matter with velocity of 10⁻³ But yeah, you could have like dark matter that's upscattered or produced in a star nearby or something like that. And those would be relativistic. That would change everything. Yeah. Which is also a good question, because then you would think about different types of targets for those dark matter sources. Okay, so just from this energy conservation equation, I get a relationship between the energy deposited and the momentum transfer, which depends on the initial velocity. And there's one way to view this, which is important, which is that, of course, this is at most, this Q dot V is at most QV. So that implies there is a minimum velocity. For a given momentum and energy deposition, there's a minimum velocity the dark matter needs to have in order to get to that part of the phase space. Or to put another way, this constraint implies that omega is less than QV minus squared over 2x.
Wait.
I'm still confused with this W. What is the W? And when you introduce it as an integrating variable, this step was a bit obscure to me. Maybe you can clarify that.
Yeah, so again, omega is the energy deposited by dark matter. And so the step where I kind of factorized things was just to split off this energy conservation between the dark matter and the system. And first to say, look at the dark matter kinematics independent of, you know, how the system responds, and then separately look at how the system responds for those same kinematics of omega and Q.
Okay.
So trying to think of just generally what's the allowed energy and momentum deposition by dark matter. And then separately, we'll see how the system responds for that given
Okay,
energy
You're
momentum.
integrating over momentum and energy deposited by dark matter. So
Yeah.
You can get that.
Exactly, yeah. Okay, so this equation that we just obtained, I'm going to draw throughout the next lecture as a series of basically parabolas. So just copy it over again. It's basically this equation, which is just an inverted parabola. And this plot shows you an example of what that looks like. So here I've just picked a particular dark matter, incoming dark matter velocity, and incoming dark matter mass of 100 GeV. And so what this constraint looks like is it'll be somewhat linear, it'll turn over, and basically you're restricted to be in this part of your phase space. This is just the dark matter scattering kinematics independent of anything else. Here I've plugged in particular numbers, but as a heuristic or just to help you remember, the maximum energy is 1/2 mv squared that's allowed. That's going to happen at Q of m chi v. So the idea of now direct detection is, given this dark matter phase space that's allowed, scattering phase space, what are possible target systems that respond in a particular Q and omega? And the example we have from nuclear recoils is given by this orange line. So for nuclear recoils, they have to respond in a particular way. They can only respond with omega equals Q squared over 2mn. For free nuclear recoils. So the idea then is this function I introduced, this S of Q omega. What it actually will look like, I won't get into deriving this, but it'll scale as the number density of your nuclei. It'll include this Helm form factor. And it will have a resonant response on this free nuclear recoil. Yes.
Why does it have to have that exact omega? Wouldn't there like be a function of the allowed omegas?
Why is it a resonant response?
Yeah.
If I'm assuming that the target nuclei are all at rest and I'm scattering off of individual nuclei, then if I deposit Q to a nucleus, then the amount of energy also has to be, just by both energy and momentum conservation, has to be Q squared over 2mn. But that's not true for more arbitrary systems.
I guess my question is, couldn't the yellow line hit the blue curve anywhere?
Oh,
You would
yes.
see a response?
Oh, absolutely. Yeah. So I was going to get to that next. So yeah, in the left plot, I'm showing you what happens if the nucleus mass is exactly the same as a dark matter mass. Then that's kind of an ideal case because the response of the system is hitting kind of right in the middle of where your dark matter scattering is. Right. And it's actually good because you're actually also able to hit the peak of the dark matter allowed kinetic energy that can be deposited. Okay, so this is great. This is what we would call kinematic matching. If it's right, goes right through the middle. I mean, it doesn't have to be exactly that, but in this case, if it is matching, then you can get as much kinetic energy out as theoretically possible. On the other hand, on the right side, I've shown the case if the dark matter mass is 100 MeV, but the nucleus mass is a lot heavier, which is 4 GeV. So in that case, the resonant response of the system is given by the orange line down here. And that's kinematically not well matched because basically you have all this available, scattering phase space that you'd like a system to respond to, but it's not, it can only respond down here. Particularly, the maximum possible kinetic energy you can get out of this interaction is all the way down here. And that's gonna, I think Jody might have covered this, that's gonna scale actually as the reduced mass between the dark matter and the nucleus squared. So I've introduced this kind of as an alternate way to think about why direct detection with nuclear recoils is so challenging for sub-GeV dark matter. It's because there's this strong kinematic mismatch between what the system wants to do and how the dark matter wants to deposit energy momentum. All this kinematic matching. On the right as kinematic mismatch. All right, so we've probably already seen a slide like this showing the constraints becoming much weaker for sub-GeV dark matter. And I will just wrap up by showing a preview of what things look like for condensed matter systems. So we'll talk next time about other types of excitations and how that response function looks like for these other types of condensed matter systems and why they would be good targets, basically why they would give good response in the particular energy and momentum range for sub-GeV dark matter scattering. So next time I'll go into more detail about both, well, primarily electron excitations, but also if there's time, something about phonon excitations and how we can probe all the way down to this much lower dark matter mass. But I will stop here for today then. Thank you.
Okay.